So now what we're going to look at is we're going to look at vector differential equations and what happens if instead of non-defective coefficient matrices, if we have defective coefficient matrices. So if our coefficient matrix happens to be defective, then we're going to need additional vectors to construct a required set of linearly independent solutions. We already have our eigenvectors, so it's going to be best for us to use those to generate associated vectors that will solve the system and still be linearly independent from the eigenvectors. And so consequently, that's what we're going to do. We're going to develop a set of vectors that we can attach to our e to the lambda t's to give us the solutions to our systems. Okay? And what we're going to suggest is we've got A. Okay? We're going to have lambda is an eigenvalue for A. And V naught is an eigenvector associated with lambda. And basically what we're going to need is that lambda is m is less than n for lambda. So basically it's the one that doesn't have a full eigenspace. Okay? So this is the one, it's got not enough eigenvectors. All right? So make sure that you're choosing that one. That's the one in particular that we've got to add an additional solution to. And we're going to suggest that our solution, so here's our suggested solution, is going to end up being x1 of t equal to e to the lambda t v1 plus tv naught. Okay? So basically, if you kind of think about this and you think about like what we were doing in higher order differential equations, anytime we wanted to actually add if we needed an additional solution and we had like repeated roots, what we did was we multiplied by some power of t or some power of x. We're doing the same thing here, right? We're going to add that power of t in order to help give us another linearly independent solution. And that's kind of our deal. That's what we're going to do. So let's actually show that this is in fact going to be a solution given a certain set of qualities or characteristics. So that's going to help us to figure out what our solution method is going to be. So we're going to take x prime, and x prime is then going to be lambda e to the lambda t, okay? And then this will be times v1 plus tv naught plus, and then this will be v naught e to the lambda t, okay? V naught e to the lambda t. Just using the product rule. So we'll kind of put that in. That's going to give me lambda e to the lambda t v1 plus lambda t e to the lambda t v naught plus v naught e to the lambda t. If I go in here now, and I'm going to separate out my t's and my non-t's. This is going to end up giving me lambda, or it's going to give me e to the lambda t, and this will be lambda v1 plus v naught plus e to the lambda t, or te to the lambda t, lambda v naught. I can actually pull these out further. I can make this e to the lambda t, and then this is going to be lambda v1 plus v naught plus t lambda v naught. Okay? A couple things that I do know. I do know that in fact that this is going to end up being, that'll end up being a v naught, because we know that v naught is actually an eigenvector. All right? So that'll end up being a v naught. And then also, in order for this to be a solution, what I'm going to need is that this is going to have to be AV1. Okay? This is going to have to be AV1. And the reason why is because we already know that this is AV naught. Right? So this is essentially, we want it to be, this is a solution if lambda v1 plus v naught equals AV1. And, right, we've got lambda v naught equals AV naught, which we already know is true. just to show you what that looks like, if we substitute back in, we're going to get e to the lambda t, right? So here's our derivative. We're going to get AV1 plus TAV naught, okay, is going to end up equaling then A times V1 plus TV naught, and that then is going to equal X prime, because that's what that equals. So if these two things are true, then we actually have the required solution that we want. So what I'm going to do is I'm actually going to kind of like give some information here. So I've got AV naught minus lambda V naught is going to equal 0. That's this first equation. And then I'm going to have that AV1 minus lambda V1 is going to equal V naught. And that's that second equation. Simplifying, we end up with A minus lambda I V naught equals 0. And I end up with A minus lambda I V1 is going to equal V naught. Now what we're going to want to do, we're going to take these two. That's going to help me to define what V naught was and what V1 is. So I'm actually going to take this, and I'm going to multiply both sides. I'm going to take A minus lambda I squared V1, and that's going to equal A minus lambda I times V naught. But this, V naught is an eigenvector, so this is going to end up equaling 0, the 0 vector. Yeah, right. So consequently, that means that one of the ways that I'm going to find V1 is it's going to be the solution to A minus lambda I squared V1 equals 0. And then we take this second one right here. That's going to be our other equation. We're going to get that A minus lambda I V1 is equal to V naught. One thing to note, we need to make sure that A minus lambda I V1 does not equal 0. Okay? It's going to end up equaling V naught. So whatever we choose, and we're going to end up choosing a V1, we just need to make sure that it's not going to end up equaling the 0 vector. So basically that it's not going to be an eigenvector for A minus lambda I. Which makes sense given the fact that if it was an eigenvector, we'd already be using it. We'd be using it already for our solutions. Okay? So our summary here, if we need one vector, or need one vector solution, what we're going to do is we're going to have our solution X is going to be of the form e to the lambda t, v1 plus tv naught, where a minus lambda I squared v1 equals 0, a minus lambda I v1 does not equal 0, and a minus lambda I v1 equals our v naught. So that's the method. That's what we're going to use. These are going to be the requirements if we need just one vector. If we need more than one, we'll generalize in just a little bit. Let's take a look at an example. All right, let's suppose that we have a equals 0, -2, 2, 4. We go in, we find that lambda, our eigenvector, is 2, and we have an associated eigenvalue, or excuse me, eigenvector of -1, 1. Okay? So in this case, what we have is we're going to actually need to find another eigenvector. So what we'll do, remember that we're going to need that a minus lambda I squared v1 should equal 0. A minus lambda I v1 does not equal 0. And a minus lambda I v1 should equal v naught. By the way, we're not going to do this until the end. All right, we'll deal with that one at the end. That's going to give us our v naught. Okay, so I'm going to start out, and I'm going to find a minus lambda I. So that means 2. 2 is our lambda. So a minus 2I is going to equal 0, or excuse me, -2, -2, 2, 2. And then we're going to go in and square it. And when we square it, what we end up with is 0, 0, 0, 0. So we need to find a vector v1 such that 0, 0, 0, 0 times v1 equals the 0 vector. Well, they all work. Like, you can pick any one that you want. So what we oftentimes do is we'll just pick the first standard basis vector. V equals 1, 0, and that totally works. By the way, you just need to find one that will actually work, all right? In this case, that means find something that's in the null space, but it's the zero matrix. Everything's in its null space, okay? All we need is we need to make sure that this thing here is true. A minus lambda I v1 does not equal 0. Well, if you remember, this is the definition, or this is how we went about finding our eigenvectors when we were finding them by hand. And so consequently what that means is that v1 cannot be equal to negative 1, 1, which it's not. Okay? If you need to check, you can always check and see that in fact negative 2, 2, 2 times 1, 0 is just going to end up giving me negative 2, 2. Done. Okay? Right? That's not equal to 0. If you need to check it, there you go. So now I'm good to go. All I need to do now is I need to actually go in and multiply. Oh, I already did it. I need to multiply v1 to get v0. So our negative 2, 2 here is going to end up being v0. So v1 we got to choose so long as a minus lambda I squared v1 did not equal 0. There it is. And we went in and we actually selected our second v0 here. Or excuse me, we multiplied a minus 2i in this case times our v1, and that gave me my v0. Okay? So my solution then, x is going to equal, we've got e to the 2t times, and it'll be the vector v1, so 1, 0, plus t, negative 2, 2. And that's my x. Call that my x2. My x1 is this one right here. So this is one solution. My second solution is the one that I got before for my eigenvector. So my overall solution, x, is going to equal c1e to the 2t times negative 1, 1 plus c2e to the 2t times 1, 0 plus t times negative 2, 2. And that's our solution. So let's say now that what we want to do is we want to solve ax equals x prime. And we'll have a equal, in this case, 2, 2, negative 1, 2, 1, negative 1, 2, 3, negative 1. We go out, we find our eigenvectors. We end up with lambda 1 equals 2, with an associated eigenvector of v1 equals 3, 2, 4. And we have lambda 2 equals 0, with an associated eigenvector v2 equal to 1, 0, 2. Turns out that lambda 2 equal to 0 has a multiplicity equal to 2. So this one here is my m equals 2. So that's going to be the one that I'm going to need the additional eigenvector for. So I'm going to suggest that my solution is going to look like this. x3 equal to e to the 0t. And this will be then v1 plus t v0. This clearly is going to equal 1. So we're all good on that end. Okay, now all we need to do is we need to figure out what v1 is and what v0 is. Remember now we need a minus lambda I squared. v1 is got to equal 0. A minus lambda I v0 cannot equal 0. Okay, and a minus lambda I v1 is going to end up equaling, excuse me, v1 will not equal 0. v1 has to equal v0. So I'm going to start out, I'm actually going to just square this matrix because lambda equals 0, so we're just looking at a minus 0i squared, which is just a squared. So we take a squared, And a squared for us now is going to look a little different. So a squared is going to equal now 6, 3, negative 3, 4, 2, negative 2, 8, 4, negative 4. We now need that a squared v is equal to 0, or v1 is equal to 0. So we need v1 to be in the null space, of a, in this case, or of a squared, pardon me, a squared. So I'm going to row reduce. So now we'll solve for that null space. The RAF of a squared is 1, 1/2, negative 1/2. So we're going to get x1 is going to equal 1/2 t plus 1/2, or negative 1/2 t plus 1/2 s. x2 will let equal t, and x3 will equal s. And so my null space x is going to equal, basically our basis vectors we're going to end up being equal to negative 1/2, 1, 0, and 1/2, 0, 1. We could choose either one of those vectors, or we could choose a linear combination of those vectors. They're all in the null space. So I'm just going to choose this one right here. I'm going to multiply it by negative 2. So I'm going to let v1 equal negative, not negative 2, but 1, negative 2, 0. All right, so that's going to be my v1. I'll confirm that it's not going to end up equaling 0 because I'm going to multiply it by a. So a times v1 is then going to equal, it's a times 1, negative 2, 0. And so when I multiply that, what I get is I get negative 2, 0, negative 4. So my solution here, call it x3, is going to equal e to the 0t, which is, we're just going to be a 1. And it'll be 1, negative 2, 0, that's v1, plus negative 2, 0, negative 4, t. Or, better yet, just 1, negative 2, 0, plus negative 2, 0, negative 4t. We'll now add that into our other two eigenvectors and eigenvalues. So we got lambda 1 equals 2, v1 equals 3, 2, 4. So that's going to be x is going to equal c1e to the 2t times 3, 2, 4, plus c2, and this is e to the 0t, which means it's just a constant, 0, and it'll be 1, 0, 2. So c2 times 1, 0, 2, plus c3, and this will be then 1, negative 2, 0, plus negative 2, 0, 4, negative 4. And that is the solution for 3 by 3, so we should expect that we have 3 linearly independent solutions, and there they are. Now what we want to do is we want to go in and we want to generalize if what we have is we actually need more than one eigenvector. We need to add, we're missing more than one eigenvector for an eigenvalue. So that is that we're missing multiples. If, say, for example, we have two eigenvalues that actually are missing eigenvectors, then what we do is we just use the same process. We can get one for each, right? Same process as we used before. On the other hand, what happens if, like, say, for example, we've got an eigenvalue that has a multiplicity of 3, but we only have one associated eigenvector? Then what I have is I'm missing two eigenvectors, right? I'm missing two solutions. I'm going to need to retrieve two of those solutions. So the process that we have here is going to actually generalize. So I'm going to write it down here, okay? But I think that probably what's best is actually getting an example, because it turns out that doing this kind of thing, just writing it out, that sort of stuff, can be a little bit. I don't know how much helps. So we start out, right? We've got x naught. This is the one that we actually have, the one that we've derived. Okay, the one that we've derived from our solutions. Then what we'll do is we can have the first one. The first one looks exactly like the one we did before. v1 plus tv naught. Then, if we need a second one, it's going to be v2 plus tv1 plus t squared v naught. Okay, and this is 1 over 2 factorial TV naught. Now notice that we add a power of t each and every time we need an additional solution. That makes sense, like a lot like what we did when we were, say, for example, using the method of annihilators. Okay, but notice also that we're going to have this 1 over 2 factorial. We'll go all the way down to 1 over k factorial if I need k different eigenvectors. Okay, or excuse me, if I need k different solutions. So we just want to be aware that that's a piece there. And for each and every value, okay, like if we had 1 over 2 factorial, right, 1 over 2 factorial t squared v naught, then we'd actually have then 1 over 3 factorial t cubed. Well, actually, this would be the v1, then the v naught, okay, and keep going and going and going until we get to our k values, okay. And then we're going to have to figure out a way to find each one of those, what we call vk, each one of those vectors. And this is what we're going to be doing. We're going to start out by taking a minus lambda I to the k plus 1th power. So like, if you remember when we were doing it with 1, we squared it. So we needed 1, so we squared it. So like if we need 5 of them, we're going to take it to the 6th power. Okay, and then find the null space for that particular matrix. We're going to make sure that when we take it to now the 5th power, right, we take 1 down, the 5th power, it doesn't end up equaling 0, and then we derive all the other vectors that we're going to need using this process, right? We're going to lose 1 power for each vector, okay, for each vector. All right, so let's just a little sketch. Let's say we need 3 additional solutions. 3 added solutions, okay? So we're going to be looking for, we're going to need to find a V3, a V2, a V1, and a V0, okay? We'll start out with a minus lambda I to the 4th V3 will equal 0. That's the first requirement that we have. Then what I'm going to do from there is also I need that a minus lambda I cubed V3 cannot equal 0. Okay, so if I drop a power, I know that that can equal 0. We drop 1 power down. Okay, I need the 3 solutions, so I'm going to take it to the 4th power, drop 1 of my powers down, know that that cannot equal 0. Then a minus lambda I cubed V3 is going to equal V0. A minus lambda I squared V3 is going to equal V1, and a minus lambda I V3 is going to equal V2. And that's how we're going to go out to find V0, V1, V2. Then our solutions are going to look like this. X1 is going to equal e to the lambda t, okay, times whatever the eigenvector is that I had originally called it V0. X2 equals e to the lambda t, and it'll be then V1 plus t V0. X3 will equal e to the lambda t, V2 plus t V0 plus 1 over 2 factorial t V0, V1 t V0, and this is t squared V0, So notice we're adding a power of t, and then we've also added in that factorial. And then V4 is equal to e to the lambda t, or x4, x4, my 4th solution, e to the lambda t, V3 plus t V2 plus 1 over 2 factorial t squared V1 plus 1 over 3 factorial t cubed V0. And that would end up being my set of solutions for that particular eigenvalue. We may have other eigenvalues that we need to find solutions for, but for that particular eigenvalue, that would give us everything we need. So let's now solve ax equals x prime. And we've got a equals negative 2, 3, 0, 0, 3, negative 2, 0, 0, 1, 0, 1, negative 1, 0, 1, 0, 1. What we'll get is we're going to get lambda 1 is going to equal 1. It's going to have a multiplicity, an algebraic multiplicity of 3, but it's only going to have v1 equal to 0, 0, 1, 0. Then we'll have a lambda 2, our second eigenvalue, being negative 5. It's going to have a multiplicity of 1. So, and it's going to be V2 is going to equal 36, negative 36, negative 5, and 6. So what we have here is we have a situation in which we're going to have to go and generate 2 additional solutions using lambda 1 equals 1. Okay? So what I'm going to do is I'm going to say, okay, well, I first want to find out what A minus I is. Okay? A minus I, and that's going to be negative 1, or excuse me, negative 3, 3, 0, 0, 3, negative 3, 0, 0, 1, 0, 0, negative 1, 0, 1, 0, 0. Okay, because we're going to subtract 1 from the diagonal. And now I'm going to have to go out, I'm going to have to find A minus lambda, or excuse me, A minus I squared. Or excuse me, A minus I cubed. Because I'm going to need 2 solutions. A minus I cubed. And then that's going to end up equaling. And it ends up equaling negative 108, 108, 0, 0, 108, negative 108, 0, 0, 15, negative 15, 0, 0, negative 18, 18, 0, 0. Remember that we're going to need to have A minus I cubed times V1 should equal 0. So we need to find something that's in the null space of A minus I cubed, right? We're going to look for a null space of A minus I cubed. So the RREF of A minus I cubed is going to end up equaling 1, negative 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay? So we'll end up with x1 equals x2, or excuse me, we'll have x1 equals t, x2 equals t, x3 will equal s, and x4 will that equal u. So my set in the null space, or my basis for the null space, is going to end up being 1, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Okay? Now what I'm going to need to do, I'm going to need to find, so this is the basis for my null space. I'm going to need to find one of those vectors, select one of them. I don't want it to be 0, 0, 1, 0. That could be potentially problematic. It would be okay. It would be fine. But why don't we just use 1, 1, 0, 0? We'll use this one right here. We know that that's in the null space. It's going to give me the 0 back. And it's not one of my eigenvectors. Okay? So now what I'm going to do is I'm going to go and I'm going to multiply that by A minus I squared. Okay? So find A minus I squared. So A minus I squared times 1, 1, 0, 0. So by the way, this is V2. V2 is going to equal 1, 1, 0, 0. We'll now multiply that by A minus I squared. That gives me 0, 0, 2, 2. And so that's going to end up giving me being V1. And now we've got to find V0. Excuse me, this is actually V0. V0 is going to be the A minus I squared. Okay, so the smallest one, A minus I squared. And then we're going to do A minus I, okay, times 1, 1, 0, 0. And that will end up giving me V1. And that ends up equaling 0, 0, 1, 1. And that's going to end up being my V1. Okay, so I now have 2 of them, okay? So on the one hand, I'm going to start out with x1 is going to equal e, and that's e to the t times, all right, 0, 0, 1, 0. So that's my first one. Then I've got x2, and that's going to be e to the t again, And it's going to be then 0, 0, 1, 1 plus t times 0, 0, 2, 2. Then x3 is going to equal e to the t, and it's going to be then, we're going to have v2, so it's going to be 1, 1, 0, 0, plus t times 0, 0, 1, 1, plus 1/2 t squared, 0, 0, 2, 2. And then finally, because we're using a 4x4, it's a 4-dimensional matrix, we're going to need x4 that's -5. So that's e to the -5t times 36, -36, -5, 6. Check that. And that's right. So our overall solution to x is going to equal c1 e to the t 0, 0, 1, 0 plus c2 e to the t 0, 0, 1, 1 plus t 0, 0, 2, 2 plus c3 e to the t 1, 1, 0, 0 plus t 0, 0, 1, 1 plus 1/2 t squared 0, 0, 2, 2 plus c4 e to the -5t 36, -36, -5, 6. And that solves your system. Okay? A couple things to note here. We'll first see that we had to use, since we were looking for two of them, we had to use a minus lambda I cubed times our vector v1 equal to 0. So we found the null space for a minus lambda I, or a minus I cubed in this case, because lambda was equal to 1. All right. And that gave us, in this case, gave us 3 of them. We could choose any one of the 3 that we wanted, as long as I really don't want to select 0, 0, 1, 0. Okay, I could have selected 0, 0, 0, 1. It would have been fine too. But I picked 1, 1, 0, 0. Any one of the ones, or any linear combination would work. And then I multiplied, I think I'm going to start out with a minus I, or, well, we'll subtract 1, a minus I squared times our selected vector is going to give me v naught. And then I'm going to drop a power, okay, down to a minus I, multiply it by my selected vector, and that will give me my v1. And then that is going to give me all the vectors that I need to construct my solution. All right, so that finishes this particular topic for finding the solutions to homogeneous systems with constant coefficient matrices, and when we have defective matrices in this case. So it's a bit more involved, but it's a process, and all you got to do is kind of keep track of the process. If you can keep track of the process, it's not too terrible, right? It's, it's go out, find eigenvalues and eigenvectors, go out and find a minus lambda I, take it to a particular power. You can use a calculator for all of this, by the way. Makes things a lot faster, a lot simpler, makes it so that you make fewer mistakes. And then, you're just going to be doing an iterative process, a lot like doing like Graham-Schmidt, okay? So this finishes the lesson. Good luck.